Imagine, if you will, the boundless canvas of our universe, a tapestry woven with billions upon billions of galaxies, each a glittering island of stars, gas, and dark matter. We gaze up at the night sky, and what we perceive is a mere fraction of what truly exists. Our journey, the quest of the sentinels of sapience, is to peer beyond these shimmering veils, to unlock the enigmas that lie not just at the beginning of time, but at the very edges of our perception. What if everything we see is just a tiny fraction of what's truly out there? What profound secrets are held within the cosmic dark, forever beyond our direct grasp? We ask ourselves, is there a final frontier, an ultimate barrier that no telescope, no theory, no human ingenuity can ever truly breach? This is our cosmic prison, a magnificent, bewildering cage, and we are about to explore its walls. So let's begin by defining the boundaries of our cosmic cell. The observable universe. This isn't the entire universe, mind you, but simply the portion from which light has had enough time to reach us since the Big Bang. It's our cosmic bubble, centered on us, stretching out in every direction. Now, here's where the first great puzzle arises. The universe is approximately 13.8 billion years old. So logically, we might expect to see light from objects up to 13.8 billion light-years away. But the true radius of our observable universe is actually a staggering 46.5 billion light-years. How can this be? How can we see things that are seemingly much older and further away than the age of the universe allows? This discrepancy, this cosmic paradox, demands an explanation. The answer to this mind-bending paradox lies in one of the most fundamental principles of cosmology, the expansion of space itself. You see, the universe isn't just a static arena where objects move around. Instead, the very fabric of space-time is stretching, expanding, carrying galaxies along with it. Imagine a rubber sheet with dots on it. As the sheet stretches, the dots move further apart, even if they aren't actively walking across the sheet. This means that light emitted by a distant galaxy 13.8 billion years ago has traveled all that time, but during its journey, the space it was traveling through has expanded. By the time that light finally reaches us, the original source of that light is now much, much further away than its initial distance, having been carried along by the expanding cosmos. The universe isn't just expanding, it's asterisk stretching. This grand, relentless expansion brings us face to face with the concept of cosmological horizons, invisible boundaries that define the limits of our perception. These aren't physical walls, but rather fundamental restrictions imposed by the speed of light and the universe's dynamic nature. They are the reason, for instance, that the night sky isn't uniformly bright, a paradox that haunted early astronomers. If the universe were infinite, eternal, and static, every line of sight would eventually terminate on a star, and the night sky would blaze with the intensity of the sun. But it doesn't. Our cosmic vision is bounded, and these horizons are the ultimate edges of what we can ever hope to see, hear, or even truly comprehend. Among these horizons, two are particularly crucial for understanding our observational limits. First, there's the particle horizon. This defines the furthest distance from which light, emitted at any point in the universe's past, has had time to reach us now. It's a sphere of knowledge, constantly expanding as more ancient light finally arrives at our cosmic doorstep. But then, there's the event horizon. This is a far more unsettling concept. It represents the furthest distance from which light emitted now asterisk will ever be able to reach us in the asterisk future. Think about that for a moment. Are there things happening right now, in this very instant, that we'll never know about, no matter how long we wait, no matter how powerful our telescopes become? The answer is a chilling yes. But perhaps the most extreme of these boundaries is the Hubble Horizon. This is the precise boundary beyond which objects are receding from us faster than the speed of light. Now, before you cry foul, remember, this isn't objects moving through space faster than light, which Einstein's relativity forbids. This is space itself, expanding so rapidly that the objects embedded within it are carried away from us at superluminal speeds relative to our reference frame. Light from these regions, no matter how fast it travels, is simply being stretched and pulled away, never to reach us. It's a cosmic current so strong that anything beyond this horizon is fundamentally and forever unobservable to us. Some parts of the universe are moving away from us faster than light itself. The very existence of these horizons is rooted in a simple yet profound cosmic truth: the finite speed of light. Light, the fastest thing in the universe, still takes time to travel. When we look at the sun, we're not seeing it as it is right now, but as it was 8 minutes and 20 seconds ago. When we gaze at Proxima Centauri, our nearest stellar neighbor, we're seeing it as it was over 4 years in the past. Every star, every galaxy, every shimmering nebula we observe in the night sky is a ghost of its former self, a relic from a bygone era. We are, quite literally, looking back in time. This cosmic time machine allows us to be archaeologists of the universe, unearthing its history with every photon we collect. This looking back in time effect isn't just a philosophical curiosity. It's a powerful scientific tool. By observing incredibly distant objects, we are essentially peering into the universe's infancy. Take, for example, the HD-1 galaxy, discovered in 2022. Located an astounding 13.4 billion light-years away, its light has traveled almost the entire age of the cosmos to reach us. When we observe HD-1, we're seeing a galaxy as it appeared just a few 100 million years after the Big Bang. It's a direct, tangible glimpse into the early formation of cosmic structures, offering invaluable clues about how our own galaxy, the Milky Way, might have begun. We can literally see how our galaxy formed billions of years ago. The ability to detect and analyze this ancient light is nothing short of miraculous, forming the bedrock of modern cosmology. Without it, our understanding of the universe's evolution would be rudimentary at best. It's through the meticulous study of light, its redshift, its spectrum, its faint echoes, that we've been able to construct and validate cornerstone theories like the Big Bang. Every photon is a messenger, carrying tales from the deepest reaches of space-time, allowing us to reconstruct the universe's dramatic narrative. Without light, we'd have no Big Bang theory at all. And perhaps no greater testament to light's crucial role exists than the accidental discovery of its most profound and ancient message. In the mid-1960s, two brilliant radio astronomers at Bell Labs, Dr. Arno Penzias and Dr. Robert Wilson, were trying to eliminate a persistent, annoying static from their horn antenna. No matter what they tried, cleaning out pigeon nests, checking equipment, recalibrating everything, a faint uniform hiss remained. It came from every direction, at all times, with no discernible source. They were baffled. They thought it was pigeon poop, but it was the echo of the Big Bang. This strange, omnipresent signal, a faint glow of microwave radiation, turned out to be the cosmic microwave background, or CMB. It was the universe's very first light, liberated from a dense, opaque early cosmos, now stretched and cooled by billions of years of expansion. They had, quite by accident, stumbled upon the most compelling evidence for the Big Bang, a ghostly whisper from the dawn of creation. The universe was once a blinding fog. What cleared it up? Imagine, if you will, the earliest moments of our cosmos, not as the clear, star-studded expanse we know today, but as an impossibly hot, dense, swirling soup. For approximately 380,000 years after the Big Bang, our universe was an opaque plasma, a superheated mixture of free electrons and atomic nuclei. Light, that swift messenger of cosmic tales, couldn't travel freely. It was constantly scattered and absorbed, trapped in this cosmic chaos, much like a beam from a flashlight trying to pierce through an infinitely dense fog. But then, a pivotal moment arrived. As the universe continued to expand, it cooled. And as it cooled, something miraculous happened. The free electrons finally settled down, combining with the nuclei to form stable neutral atoms. Suddenly, the universe became transparent. Light, for the very first time, was free to stream across the cosmos, unimpeded. This ancient light, no longer scattered, is what we call the cosmic microwave background, or CMB. It's an awe-inspiring echo, a direct photograph of the universe, just as it became visible. This faint cosmic glow is how we know the universe's exact age. So what exactly symbols this cosmic microwave background, this ancient glow? It's a form of electromagnetic radiation, specifically microwaves, permeating every corner of the observable universe. Today, its temperature is a mere 2.725 degrees above absolute zero, a chilly whisper of its fiery past. But its uniform presence, detected from every direction, at an astonishing distance of 13.8 billion light-years, is the most profound confirmation of our universe's age. It tells us that everything we see, everything we know, burst forth from a single cataclysmic event, and that event happened precisely 13.8 billion years ago. It's not just an ancient artifact, it's a cosmic clock, ticking away since the moment light first escaped its primordial prison. And it serves as the ultimate backdrop to our entire cosmic story, a constant, silent reminder of where we came from. The universe's expansion literally hides its first light from us. But if the CMB is everywhere, a relic of the Big Bang, why can't we simply see it with our own eyes? It's a natural question, given its profound significance. The answer lies in the relentless, ongoing expansion of space itself. When that ancient light first broke free, it was incredibly hot and energetic, appearing as visible light. But as the universe expanded over billions of years, the very fabric of space-time stretched these light waves. Imagine stretching a rubber band with a wave drawn on it. The wave gets longer. This cosmic stretching caused the light's wavelength to increase dramatically, shifting it from visible light, through infrared, and finally into the microwave spectrum. Our human eyes simply aren't equipped to detect microwaves. So, while the CMB is all around us, bathing every inch of the cosmos, it remains invisible to our natural senses, a silent hum of creation only detectable by specialized instruments. We're literally seeing the universe as it was, just moments after its birth. Despite its invisibility to the naked eye, the cosmic microwave background is far from insignificant. For us, the sentinels of sapience, it's more than just a faint signal. It's a direct, unadulterated window into the universe's earliest moments. It's like finding a pristine archaeological site, perfectly preserved, offering an unparalleled view into the very dawn of existence. The CMB is the ultimate proof of the Big Bang scenario, confirming a hot, dense beginning followed by expansion and cooling. It provides insights into the universe's fundamental composition, its geometry, and the seeds from which all future cosmic structures would grow. Scientists, poring over CMB data from powerful telescopes and laboratories, are essentially looking through a crack in time, peering back to when the universe was just a toddler, barely 380,000 years old. It is, perhaps, the most profound insight into cosmic history we possess. This spotted map is the blueprint for every galaxy you see. When scientists analyze the cosmic microwave background, they don't just see a uniform glow. Instead, they produce stunning, colorful sky maps filled with tiny, subtle temperature fluctuations, hot and cold spots scattered across the cosmic canvas. These aren't random splotches. They are the most ancient structures we can observe, the primordial seeds of everything that came after. These minuscule temperature differences, mere fractions of a degree, represent areas of slightly higher or lower density in the early universe. The slightly denser, hotter regions had a stronger gravitational pull, acting as cosmic magnets, slowly accumulating more and more matter over billions of years. Conversely, the colder, less dense regions became the vast, empty voids we discussed in our last chapter. These tiny quantum fluctuations, amplified by the universe's rapid inflation, were the gravitational starting points for every star, every galaxy, and every galaxy cluster we see today. It's truly the universe's original blueprint, written in light. The CMB proves our universe isn't curved. It's flat. The patterns embedded within the CMB map offer far more than just a baby picture of the universe. They provide crucial evidence for its fundamental geometry. Imagine drawing a triangle on a flat piece of paper versus drawing one on a curved surface, like a sphere. The angles would add up differently. Similarly, the apparent size of the hot and cold spots in the CMB map tells us about the curvature of spacetime on a cosmic scale. What we've observed is that the largest fluctuations in the CMB, those that span approximately 1 angular degree across the sky, appear exactly as they would in a spatially flat universe. This observation is a powerful confirmation of the flat model of the universe, meaning that on the grandest scales, parallel lines would remain parallel, and the angles of a cosmic triangle would always add up to 180 degrees. It's a profound insight, derived from the faint echoes of creation itself. The CMB showed us that 95% of the universe is made of something we can't see. Perhaps one of the most astonishing revelations gleaned from the CMB data concerns the very composition of our universe. In 2003, a team led by Dr. David Spergel used detailed CMB measurements to refine our understanding of the cosmic inventory. And what they found was truly mind-boggling. It turns out that the ordinary matter we see and interact with, the atoms that make up stars, planets, and even us, accounts for only about 5% of the universe's total mass energy. The remaining 95% is composed of two mysterious, invisible entities: dark matter and dark energy. Dark matter, making up about 27%, provides extra gravitational pull, holding galaxies together. Dark energy, a staggering 68% of the universe, is the force driving its accelerating expansion. The CMB's subtle patterns provided the most robust evidence for these enigmatic components, forcing us to confront the fact that most of our universe remains a profound, unseen mystery. We know exactly how fast the universe is expanding, thanks to this ancient light. Beyond revealing the universe's age, geometry, and composition, the cosmic microwave background has also allowed scientists to precisely measure the rate at which our universe is expanding. By analyzing how the CMB photons have been stretched and cooled since their emission, we can deduce the current expansion rate, known as the Hubble constant. While there are still slight discrepancies between different measurement methods, the CMB provides a consistent value. This constant tells us that for every megaparsec of distance, roughly 3.26 million light-years, the universe is expanding by approximately 42 miles per second. That's about 67 kilometers per second per megaparsec. This precise quantification of cosmic expansion is a testament to the power of the CMB as a cosmic ruler, allowing us to gauge the dynamics of the universe with remarkable accuracy, all from the faint echoes of its birth. Our cosmic view is trapped by two invisible walls, the CMB and space itself. As we reflect on the profound insights offered by the cosmic microwave background, it becomes clear that this ancient light, along with the various cosmic horizons we explored earlier, collectively define the ultimate limits of what we can directly observe from Earth. The CMB represents a fundamental boundary in time, the earliest moment from which light could reach us, a literal wall of fog before which our optical telescopes are blind. We can't see through the CMB because before it, the universe was opaque. And then we have the space horizons, boundaries dictated by the finite speed of light and the accelerating expansion of the universe, which limit how far we can ever peer into the spatial expanse. Together, these two phenomena act as dual limits to our cosmic vision, framing our perspective within a finite sphere of knowledge. We are, in essence, looking out from a small window, its frame defined by the very physics of our universe. Our cosmic horizon is always moving, but there's a part of the universe we'll never see. While the cosmic microwave background offers us a fixed historical boundary, the particle horizon, which defines the edge of our observable universe, is a dynamic entity. It expands over time. As light from increasingly distant regions finally reaches us after billions of years of travel, our observable universe grows, revealing more and more of the cosmos that was once hidden. With every passing moment, with every new, more powerful telescope, we push the boundaries of this horizon, unveiling galaxies and structures that were previously beyond our reach. Yet, despite this continuous expansion of our observable sphere, there remains a fundamental, unyielding truth. We will never, ever directly see what truly lies beyond this particle horizon. The universe is vast, perhaps infinitely so, and the light from those most distant, unobservable realms will simply never have enough time to reach us. It's an ultimate boundary, a constant reminder of the humbling scale of the cosmos and the inherent limits of our direct perception, pushing us to find other, more ingenious ways to understand the unseen. We've spoken of the limits of light, of the cosmic veils that hide so much from our direct gaze. But what if we could develop new senses, new ways to peer through the fabric of space-time itself? Enter the neutrino, a particle so elusive, so ghostly, it might just be our key to unlocking the unseen universe. These tiny fundamental particles interact so minimally with matter that they can pass straight through entire planets, even stars, without a whisper. Imagine the possibilities. Particles born in the heart of distant, ancient supernovae, or from the earliest moments of the Big Bang, traveling unimpeded across billions of light years, carrying information that light simply cannot. They are the ultimate cosmic messengers, whispering secrets from beyond the edge of our visible universe. The promise of neutrino detection is a beacon of hope for us, the sentinels of sapience, while current neutrino observatories, vast underground tanks filled with super-pure water or ice, have already given us incredible insights into the sun and distant cosmic events. Their full potential is yet to be realized. Imagine future ultra-sensitive detectors, perhaps spread across the solar system, capable of catching even the faintest neutrino signals. Such technology could finally allow us to map regions of the universe forever shrouded in darkness by the CMB, revealing what truly lies beyond our current cosmic horizon. It's a grand ambition, but one that fuels our relentless curiosity. But neutrinos aren't our only hope. Another revolutionary sense has emerged: gravitational waves. These are not particles, but ripples in the very fabric of space-time itself, caused by the most violent and energetic events in the cosmos. Think of them as waves of time propagating at the speed of light, generated by titanic cosmic collisions, black holes merging, neutron stars spiraling into each other, or perhaps even echoes from the Big Bang itself. Unlike light, which can be absorbed or scattered, gravitational waves pass through everything, carrying pristine, invaluable data from events that would otherwise be completely invisible to us. They offer a fundamentally new way to hear the universe. The year 2016 marked a triumph for humanity, a moment when we truly began to listen. Scientists at MIT, using the Laser Interferometer Gravitational Wave Observatory, or LIGO, made the groundbreaking first detection of gravitational waves. The signal was fleeting, a mere chirp, but it was unmistakable. The sound of two massive black holes colliding and merging over 1.3 billion light-years away. This wasn't just a theoretical concept anymore. It was real, concrete proof. This incredible achievement demonstrated the power of gravitational waves to reveal extreme cosmic events and distances, giving us a new window into the universe's most dramatic moments. For the first time, we truly heard the cosmos. So, as we push the boundaries of technology, we are developing new senses, new ways to perceive the universe. Both gravitational waves and neutrinos are absolutely crucial for expanding our knowledge beyond the veil of the visible universe. They represent humanity's audacious attempt to overcome the inherent limits of light-based observation. Our relentless scientific endeavor, our insatiable drive to build more sensitive instruments and devise cleverer experiments, is the key. It's how we continue our cosmic quest, forever striving to see, hear, and understand more of the universe than ever before, even the parts that seem forever out of reach. Yet, even with these incredible new tools, we face a persistent, undeniable obstacle: the relentless expansion of the universe. Imagine trying to observe something that is constantly, actively moving away from you, not just through space, but because the very space between you and it is stretching. That's our cosmic reality. All space objects, beyond our immediate galactic neighborhood, are moving away from each other, and the further they are, the faster this recession accelerates. It's an inherent, unchanging nature of the cosmos, a barrier that no telescope, no matter how powerful, can truly overcome for direct observation. The universe itself is against us. This accelerating expansion brings us back to a chilling concept, the event horizon. Currently, it lies about 16 billion light-years away from us. Think of it as a cosmic point of no return. Any signal, any message, any light emitted now from beyond this boundary will never reach us, no matter how long we wait. The space between us and that distant point is expanding faster than light can travel. And here's the truly unsettling part. Even if an object is currently visible to us, its future signals, sent later, might be lost forever if it crosses this horizon. It's a critical barrier to any hope of future cosmic interaction, a boundary that guarantees ultimate isolation. This means our future could be one of profound cosmic isolation. As the universe continues its accelerating expansion, any signals we emit will eventually stretch and dilute, becoming utterly undetectable to any distant civilizations. And the same will be true for their messages to us. We might already be experiencing this, a profound silence from a universe that is simply moving away too fast for its whispers to reach us. In the far, far future, even our nearest galactic neighbors, like Andromeda, will be pushed beyond our event horizon, becoming forever unreachable, forever unseen. We are witnessing the slow, inevitable severing of cosmic connections, a deepening existential loneliness. In tens of billions of years, the event horizon and the Hubble Horizon will merge, forming a single, inescapable cosmic limit. Beyond this boundary, all light will disappear, leaving our local patch of the universe in ultimate, profound darkness. Imagine a future where the night sky is utterly black, devoid of distant galaxies, a silent, starless void. It's a foreboding vision, a future of ultimate cosmic loneliness. But even then, we, the sentinels of sapience, will persist. The universe holds infinite secrets, and our curiosity remains unyielding. We hold on to the hope that future generations, armed with advanced technologies like neutrino and gravitational wave detectors, will find ways to manage these limitations, to peer through the encroaching darkness, if not to eliminate it entirely. For even as the universe closes in, the spirit of human exploration, our quest to understand, will never be extinguished. We move now from the cosmic prison to the hourglass of existence, as we prepare to confront the ultimate end of all things. For millennia, we, the sentinels of sapience, have gazed skyward. We've charted the stars, deciphered the dance of planets, and with ever-growing telescopes, peered into the very cradle of our universe. We've unraveled the story of its beginning, the explosive genesis that birthed all matter and energy. But did we ever dare to think about the end? Not the end of our fleeting human existence, not even the demise of our solar system, but the ultimate conclusion of everything? The end of time itself? This is the grandest, most profound question we can ask. A cosmic mystery that transcends our own brief flicker of consciousness. It's our deepest quest. A journey not just through space, but through the unimaginable stretches of cosmic time, towards a future that will redefine everything we thought we knew about existence. Join us as we face the inevitable. Our journey begins not with distant stars, but with our home, Earth. For the last 700 years, the Holocene epoch has been a period of remarkable stability, allowing our civilization to flourish, our cities to rise, and our knowledge to expand. We cultivated the land, tamed rivers, and built empires under its benevolent skies. But then, squiz changed. Our thirst for resources, our relentless expansion, and our technological prowess began to leave an indelible mark. We pumped carbon into the atmosphere, altered landscapes beyond recognition, and triggered a cascade of climate change, extreme weather, and biodiversity loss. Scientists now declare we've entered a new geological epoch, the Anthropocene. This is the era shaped by our colossal, often detrimental influence. It forces us to confront a haunting question. As we trace Earth's future, how much of its fate is written by the cosmos, and how much by our own hands? What legacy will we leave? Fast forward to the year 2500. A subtle, yet profound shift is underway beneath our feet. Earth's magnetic poles are preparing to flip. This isn't a sudden, catastrophic event, but a gradual weakening and reversal of our planet's protective shield. It's a natural geophysical process, one that has occurred many times in Earth's deep past. But for our technologically advanced civilization, it presents immense challenges. GPS systems will falter, power grids will be vulnerable to solar storms, and our satellites will face increased radiation. We will be forced to adapt, to innovate, to develop new technologies and strategies, to navigate a world where the very compass of our planet has been reset. It's a cosmic reset, reminding us that even our home world has a will of its own. Amidst Earth's internal shifts, the cosmos continues its majestic dance. In the year 4385, the iconic comet Hale-Bopp, last seen in our skies in 1997, makes its grand return. Its luminous tail, a celestial reminder of the solar system's icy depths, once again graces our night sky, a fleeting moment of astronomical beauty for future generations. Then, around the year 8000, we witness a more dramatic, yet distant, spectacle. A supernova explosion in a galaxy far, far away. The light, traveling for thousands of years, finally reaches us, a sudden, brilliant flash in the darkness. It's a stark reminder of the universe's dynamic, ever-changing nature, a violent birth of new elements that will eventually form new stars and planets, far beyond our reach. But as we gaze outwards, the consequences of our past actions continue to unfold closer to home. By the year 5000, the dire predictions of climate scientists have become a grim reality. The polar ice caps, once vast bastions of white, have melted almost completely, unleashing a deluge upon our coastal regions. Global sea levels have risen dramatically, redrawing the maps of continents. Iconic cities, once bustling metropolises, now lie partially submerged, their skylines reduced to ghostly silhouettes against the tide. Coastal towns, once vibrant communities, have been swallowed whole, becoming relics of a lost world beneath the waves. It's a somber testament to the irreversible impact of our choices, a chilling reminder that our legacy can be as destructive as it is creative. Just a millennium later, in the year 6000, a new, more immediate threat emerges from the vastness of space. A colossal asteroid, its trajectory locked, looms on the horizon. This isn't a distant, theoretical possibility. It is a date with destiny. Despite all our advanced technology, our efforts to deflect or destroy it prove futile. The collision is inevitable. The impact will be cataclysmic, unleashing energy orders of magnitude greater than any event in recorded human history. It will profoundly alter life on Earth, reshaping landscapes, triggering global seismic events, and shrouding the planet in a prolonged, suffocating winter. It's a stark, brutal reminder that even if we survive our own follies, the universe holds its own, unforgiving challenges. Another 100 million years pass, and Earth's fate is sealed. Around 1.1 billion years in the future, the Adak green carpet that once adorned our planet has withered and died. Lush forests, vibrant fields, and teeming ecosystems are replaced by desolate, barren landscapes, cracked and parched under the sun's relentless glare. Even more critically, the delicate balance of our atmosphere collapses. As photosynthesis ceases, the oxygen levels plummet, making the air thin and utterly unsustainable for the complex life forms that once thrived here. Earth becomes a ghost of its former self, a withered, lifeless sphere, slowly suffocating under the weight of its star's relentless evolution. The vibrant blue-green marble is now a dull, reddish-brown husk, By 1.3 billion years into the future, the final vestiges of Earth's habitability vanish. The increasing solar heat intensifies, turning our planet into an inferno. The vast oceans, those magnificent bodies of water that defined Earth as the blue pearl of the cosmos, begin to boil. Slowly, inexorably, they evaporate, releasing immense amounts of steam into the atmosphere, only for that steam to be stripped away by the ever-intensifying solar winds. What remains is a parched, desolate surface, a planet utterly devoid of liquid water. This is the moment of ultimate loss, the final act in Earth's transformation into an uninhabitable, desiccated world, a barren sphere silently orbiting its increasingly hostile star. The ultimate catastrophic end for our home world arrives approximately 7.5 billion years from now. The Sun, having exhausted the hydrogen fuel in its core, begins to fuse helium, causing it to swell dramatically into a monstrous red giant. Its outer layers expand outwards, engulfing Mercury and Venus in its fiery embrace. Then, with terrifying inevitability, it reaches Earth. Our planet, now a charred, lifeless rock, is consumed by the expanding star. It's a dramatic and absolute destruction, marking the definitive end of Earth's existence. Our home, the crucible of life and consciousness, vanishes into the heart of its transformed star, a fleeting memory in the grand, indifferent cosmos. After its fiery, destructive red giant phase, the Sun continues its stellar life cycle, though in a much quieter, more subdued form. Approximately 10 billion years from now, having shed its outer layers, our star is reborn as a white dwarf. This is a small, incredibly dense remnant, roughly the size of Earth, but still containing half the Sun's original mass. It's no longer actively fusing elements. Instead, it slowly cools and fades, radiating away its residual heat over trillions of years. Our once mighty Sun becomes a weak, cooling ember, a silent spectator in a solar system it once dominated, now devoid of planets. It's a melancholic, quiet aftermath to a spectacular, violent end. As we journey through these unfathomable timescales, witnessing the slow, inevitable demise of our home and our star, we are forced to confront the profound humility of our place in the universe. Humanity, for all its colossal influence on Earth, for all its triumphs and tragedies, its civilizations and its science, is but a fleeting memory in the grand cosmic timeline. Our planet, once teeming with life, is gone. Our Sun, the source of our existence, is a dying ember. Will any trace of our existence persist in this cosmic aftermath? Perhaps a faint radio signal, traveling for billions of years, now so stretched and diluted that it's indistinguishable from background noise. Or perhaps, simply, the enduring spirit of curiosity that drove us to ask these questions in the first place. This journey to the end of Earth and Sun is not just a scientific prediction, it's a profound reflection on legacy, impermanence, and the search for meaning in a universe that is both magnificent and utterly indifferent to our brief, vibrant flicker. We've journeyed through the fiery demise of our own Sun, a spectacle of cosmic destruction and rebirth. But what about the rest of the universe? What about the countless stars that still pepper the vast canvas of night? Let us fast forward, not just billions, but a staggering asterisk 100 trillion years into the future. Imagine, if you can, a universe where the relentless engine of stellar fusion has finally sputtered. The last red dwarf, a tiny, tenacious ember, has exhausted its hydrogen fuel and faded into the void. A deep silence, colder and more profound than any we can comprehend, falls across the cosmos. One by one, the remaining stars, those that haven't been swallowed by black holes or flung into the intergalactic abyss, simply wink out. This is the beginning of the end for starlight, a chilling darkness descending upon the universe, ushering in an era of cosmic twilight. Imagine a universe where every star eventually dies, leaving only darkness. From the twilight of stars, we plunge deeper into the cosmic night. Move forward another quadrillion years, and we find ourselves in an era of true desolation. The universe's temperature has plummeted to an unimaginable low, a mere fraction above absolute zero. This is the cosmic winter, a time when the last faint glows have vanished, and the very concept of warmth becomes a forgotten relic. The era of starlight, once the vibrant heartbeat of existence, has ended completely. What remains is a cosmic graveyard, vast and silent, populated only by the cold, dark husks of what once burned so brightly. The universe becomes a frozen, lightless graveyard, billions of years from now. Our journey continues through a universe now *10 quadrillion years old. This is the age of degeneration, an interim state where the dominant celestial bodies are no longer stars, but their ghostly remnants, white dwarfs. These are the shrunken, cooling cores of stars like our Sun, no longer fusing hydrogen, but still radiating a faint, residual heat. They drift through the desolate expanse, like dying embers in an endless night. It's a ghost universe echoing the past grandeur of galaxies and stars, a somber testament to a vibrant era long since past. What's left to light up the universe after all the stars die? Yet, even in this age of decay, the fundamental forces of the universe persist. Gravity, the sculptor of galaxies, still holds sway. It continues its slow, relentless dance, occasionally ripping planets from their orbits around dying white dwarfs, sending them hurtling into the void. And in truly rare dramatic events, rogue white dwarfs might collide, igniting a brief, ultra-bright supernova, a spectacular, fleeting echo of the universe's more vibrant past, a final, defiant flicker of light in the encroaching darkness. Even in a dying universe, gravity creates spectacular, rare bursts of light. But even the white dwarfs are not eternal. Over trillions of years, their residual heat slowly radiates away into the cold, empty vacuum of space. They cool, they shrink, their faint glow dims, until finally they become utterly invisible. These are the black dwarfs. Theoretical, for the universe isn't old enough for any to have formed yet, marking the ultimate end state for most stars. No light, no heat, just cold, dense, dark lumps of matter, indistinguishable from the blackness around them. This is the complete cessation of stellar light, a plunge into ultimate cosmic quiet. Every star, even our Sun, will one day turn into an invisible black dwarf. As if the cold, dark silence weren't enough, we must now confront a more fundamental dissolution. The universe's relentless expansion continues to stretch space-time itself, reaching a point where even the most basic building blocks of matter become unstable. We're talking about asterisk proton decay, charge. According to some grand unification theories, protons, the very particles that make up atoms, and thus everything we know, are not truly stable. Given enough time, an almost unimaginably long time, they could decay into lighter particles, like neutrinos and photons. This isn't just stars dying. This is matter itself, slowly, eerily disintegrating, turning everything into faint wisps of energy. What if the very building blocks of everything, even you, eventually fall apart? After the stars have faded, and even the protons have decayed, what remains? Only the universe's ultimate gravity wells, black holes. This is the era of black holes, a period lasting for an almost incomprehensible number of years, where these enigmatic gravitational monsters become the last guardians of mass. With black dwarfs gone and matter disintegrated into fundamental particles, the cosmos is primarily populated by these silent, swirling voids. Some are stellar mass black holes, remnants of long-dead massive stars, while others are supermassive, the colossal hearts of vanished galaxies. A vast, dark cosmic canvas with numerous, swirling black holes, some small, some gargantuan, the universe's last giants. Among these silent giants, the supermassive black holes reign supreme. These are the colossal remnants of the centers of galaxies, having grown to incredible sizes over eons, devouring everything in their path. They represent the universe's final, grand structures, still slowly absorbing any residual matter and energy that drifts into their crushing gravitational fields. In these unimaginably distant epochs, as they slowly accrete the last vestiges of existence, they might emit faint gravitational waves, ripples in spacetime itself. These are the last sounds of the universe, silent whispers of dying black holes, a profound and eerie symphony of ultimate cosmic finality. But even black holes, these ultimate devourers, are not eternal. Thanks to the groundbreaking theoretical work of Dr. Stephen Hawking, we understand a process known as Hawking radiation. This incredible concept suggests that black holes slowly lose energy and mass over vast, unfathomable timescales, radiating particles until, eventually, they evaporate completely. The largest supermassive black holes could take quadrillions of years to vanish, but vanish they will. This marks the death of the universe's last major objects, leaving behind a void of true nothingness, a profound emptiness where all structured existence has finally dissipated. Even black holes aren't forever. Stephen Hawking predicted how they'll vanish. As we contemplate these ultimate ends, we must remember that the universe's fate ultimately hangs in a delicate balance between two mysterious, unseen forces, dark energy and dark matter. Dark energy, as we've discussed, is the enigmatic force accelerating the universe's expansion, pushing galaxies apart. Dark matter, on the other hand, is gravity's invisible counterbalance, providing the gravitational attraction that pulls matter together, forming galaxies and clusters. The precise interplay, the cosmic tug-of-war between these two dominant, yet poorly understood, components will determine which of the universe's ultimate fates comes to pass. A slight shift in this delicate balance, and everything changes. The universe's ultimate fate depends on a cosmic tug-of-war between invisible forces. One dramatic scenario, if dark matter were to ultimately outweigh dark energy, is the asterisk, das Big Crunch. Imagine the universe, after its long expansion, slowing down, then reversing course. Gravitational attraction would begin to pull all matter back together. Galaxies would rush towards each other, colliding in spectacular fashion. Temperatures would rise, space would shrink, until all the universe's matter and energy were compressed back into an infinitesimal, superhot point, a singularity, much like the one from which it began. But this isn't necessarily an end. Some theories suggest this singularity could then trigger another Big Bang, beginning a new cycle of existence. A universe reborn from its own ashes, an endless cosmic heartbeat. What if our universe collapses back into a tiny point, only to be reborn again? From the scorching fury of our own sun-consuming Earth to the chilling desolation of a universe succumbing to the Big Crunch, we've witnessed the grand, terrifying, and awe-inspiring end of all things. Humanity, in this vast cosmic timeline, exists for but a fleeting moment, a blink in the eye of eternity. Our legacy, our dreams, our very existence will one day be but a memory, swallowed by the inevitable march of cosmic forces. Yet, in this immense, cyclical dance of creation and destruction, we find a profound revelation. In a universe of infinite possibilities, the end is often just another beginning. Our contemplation of the end of time isn't about despair, but about understanding our place in this grand, beautiful, and eternal story. The universe ends, but does that mean we end too? Or is it just another beginning? We've journeyed through the deep past, witnessed the birth of time itself, and peered into the unimaginable twilight of cosmic existence, billions upon billions of years from now. But what if we could tame time? What if we could fast forward, not to the ultimate end, but to a time frame within our grasp, a mere 100 million years into the future? What would the universe look like then? What grand cosmic dramas would unfold? And more importantly, what role might humanity, play in shaping a future we can scarcely comprehend? This isn't just a thought experiment. It's an invitation to explore a future where our ambition might finally contend with the universe's relentless march toward oblivion. In this relatively short span of 100 million years, the universe won't undergo cataclysmic shifts on a grand scale, but subtle, profound changes will ripple across the cosmos. For starters, we would witness the slow disappearance of all the universe's most massive, brilliant stars. Those cosmic titans, burning through their fuel at a furious pace, will have lived their short, spectacular lives, collapsing into neutron stars or black holes, leaving behind only ghostly nebula, beautiful, shimmering shrouds of gas and dust. Our own sun, meanwhile, will have subtly but relentlessly heated up, becoming roughly 1% brighter and warmer. A seemingly small change, but one that would render Earth uninhabitable, turning our blue marble into a parched, unforgiving desert. But here's where our human ingenuity comes into play. What if, within those 100 million years, we, the sentinels of sapience, had mastered the ultimate craft, stellar engineering? Imagine the power to asterisk tame the stars themselves. By then, our science might allow us to replenish stellar fuel, perhaps by directing vast streams of hydrogen and helium to dying stars, or even influencing the nuclear reactions within their cores to extend their lifespans. We could potentially turn a dim red dwarf into a brighter, more stable sun, or prevent a star from ever becoming a destructive red giant. This isn't just about survival. It's about rewriting the very rules of cosmic evolution. With such godlike power over the stars, the promise for human civilization would be nothing short of utopian. We could create new habitable conditions on countless planets that were once barren and frozen, turning distant ice worlds into lush oases. Imagine vast Dyson spheres, colossal structures built around stars, harvesting their immense energy to power entire interstellar civilizations, ensuring an endless supply for billions of years. This incredible energy could also be used to preserve planetary resources, preventing their natural decay and allowing humanity to flourish across the galaxy, truly becoming a multistellar species. Yet with such immense power comes equally immense peril. Our attempts to tame the stars could inadvertently accelerate their cosmic aging. By collecting and concentrating stellar fuel, or even by artificially boosting nuclear reactions, we might inadvertently cause stars to burn through their lifespans at an unnatural rate. This could make life near those stars intensely dangerous, causing them to flare and die prematurely. On a galactic scale, our interventions could rapidly age entire star clusters, turning vibrant nurseries into desolate graveyards. A chilling testament to humanity's hubris and the unintended consequences of playing God. Beyond our own potential interventions, the natural cosmic dance of galaxies will continue its majestic, slow-motion ballet. Over 100 million years, smaller galaxies will continue their inexorable gravitational pull towards larger ones, leading to mergers and the formation of new, often distorted, galactic structures. Our own Milky Way, for instance, will have moved significantly closer to its colossal neighbor, the Andromeda Galaxy. While the full, spectacular collision is still billions of years away, the gravitational embrace will have tightened, the first tendrils of galactic matter stretching out like cosmic fingers, a prelude to the grand, inevitable merger. But even as new, larger galaxies form, a slow fade will begin to settle over the cosmos. The once bright, vibrant galaxies of the early universe will gradually dim. Massive stars, with their short, fiery lives, will have long since died, leaving fewer and fewer new stars to be born. The precious gas and dust, the raw material for stellar nurseries, will be depleted or locked away in stellar remnants. Eventually, these magnificent spirals and ellipticals will become ghost-like, their brilliant arms fading, until only the faint, scattered glow of long-lived red dwarfs and the silent, hungry presence of black holes remain. And then, there's the relentless expansion of the universe itself. Within 100 million years, the galaxies beyond our local group will become even harder to observe, receding into the cosmic distance. Distant clusters, once visible with powerful telescopes, will shrink to faint smudges, almost invisible against the deepening cosmic night. This isn't just objects moving through space. It's space itself, stretching, pulling everything further apart. We know this acceleration is driven by dark energy, a mysterious force that causes the universe to expand at an astonishing rate, approximately 44 miles per hour for every 3.26 million light-years of distance. This unseen force is the ultimate driver of our cosmic fate, and its implications are dire. If dark energy continues its relentless acceleration, one of the most probable scenarios for the universe's ultimate end is heat death. In this chilling future, the expansion rate will increase so dramatically that galaxies will no longer be able to merge, pulled apart by the stretching fabric of space-time. Star formation will dwindle to nothing. All matter and energy will become so thinly spread, so utterly dissipated across an ever-growing empty void, that the universe will reach a state of maximum entropy. It will be a vast, cold, dark expanse where no energy gradients exist, no work can be done, and no life can ever arise. An ultimate, eternal stillness. But even more terrifying than the slow, cold embrace of heat death is the possibility of the Big Rip. Imagine dark energy's accelerating push becoming so overwhelming, so utterly dominant, that it begins to overcome even the fundamental forces holding matter together. First, galaxies would be torn apart, their stars flung into the void. Then, stars and planets themselves would disintegrate, ripped from their orbits, and violently atomized. Finally, in the most catastrophic act of all, even atoms themselves would be torn apart, the very fabric of existence unraveling into a chaotic soup of elementary particles before those too are ripped into non-existence. A complete, total cosmic annihilation. Adding another layer to this cosmic dread is the theoretical concept of proton decay. Based on grand unification theories, some physicists speculate that protons, the stable building blocks of all atomic nuclei, might not be truly immortal. Given enough time, an unimaginably vast amount, far exceeding the current age of the universe, protons could spontaneously decay into lighter particles like neutrinos and photons. While this wouldn't necessarily rip the entire universe apart like the Big Rip, it would slowly, subtly erode all matter. Atomic nuclei would destabilize, disrupting galactic evolution, and ensuring that even the most resilient stellar remnants would eventually fade into nothingness. But perhaps the most absolute and terrifying scenario is vacuum decay. To understand this, we must consider the Higgs field, which permeates all of space and gives particles mass. It exists in what we call a false vacuum state, a stable, but not most stable energy level. If, by some quantum fluctuation, our universe were to transition to a true vacuum state, a bubble of this new, lower energy state would spontaneously appear somewhere in the cosmos. This bubble would then expand at the speed of light, converting everything it encounters, every star, every galaxy, every particle, every fundamental force, into something utterly alien and unrecognizable, annihilating all matter and fundamental particles in an instant, without warning or escape. And so we stand at the precipice of an unwritten cosmic future. Whether it's the slow chill of heat death, the violent tear of the Big Rip, the subtle erosion of proton decay, or the absolute annihilation of vacuum decay, the universe will undoubtedly transform into something profoundly different, something beyond our current comprehension. Yet, even in the face of such overwhelming cosmic threats, our journey continues. We, the sentinels of sapience, will persist in our quest, making outstanding discoveries, pushing the boundaries of what is known. Perhaps, one day, we will reveal the full, terrifying, and awe-inspiring history of the universe, from its enigmatic beginning to its ultimate, inevitable end. But before we gaze further into those ultimate cosmic fates, let us pull back from the accelerating expansion and turn our attention to another profound mystery, one that challenges our very understanding of cosmic structure, the Great Void. Imagine a hole in the universe so vast, so incredibly empty, that it would take 330 million years to cross at the speed of light. This isn't a black hole, or a region obscured by dust. It's an unfathomably immense stretch of space, almost entirely devoid of galaxies, stars, or even significant amounts of dark matter. It feels like a breach in the cosmic design, a puzzle that stirs our imagination and pushes us to question everything we thought we knew about the universe's grand architecture. For centuries, early astronomers, peering through their rudimentary telescopes, saw a universe teeming with stars, a seemingly uniform spread of light. They meticulously mapped the heavens, slowly realizing our sun was just one star in a vast collection, our Milky Way. But as technology advanced, and in the early 20th century, we finally grasped the incredible truth. Our galaxy was just one of billions, each a swirling island of stars. Yet even then, as we began to map these distant island universes, a strange pattern emerged. Vast, dark regions seemed to separate these glittering clusters. It was as if the universe, far from being uniformly distributed, was beginning to reveal hints of colossal emptiness, prompting the first whispers of cosmic voids. For centuries, we gazed up at the stars, marveling at their brilliance. But our perspective was limited. We saw a tapestry of light, but didn't grasp the true, three-dimensional architecture of the cosmos. That began to change in the 1970s and 80s, when astronomers, armed with new redshift studies, started to map the universe not just in two dimensions, but across vast cosmic distances. What they unveiled was nothing short of astonishing. Instead of a uniform scattering of galaxies, we discovered a vast, intricate structure, an immense cosmic web woven from glowing filaments of galaxies and clusters. And, nestled within this luminous network, were colossal, dark spaces, regions of profound emptiness where galaxies were almost entirely absent. These were the voids, and they challenged our very notion of cosmic design. The universe, we realized, isn't just stars. It's a giant cosmic web with massive, empty holes. The initial discoveries of these voids were just the beginning. As digital technology advanced and telescopes grew ever more powerful in the late 20th and early 21st centuries, our ability to map the universe in intricate detail exploded. Projects like the Sloan Digital Sky Survey began to paint astonishing 3D visualizations of the cosmos. These weren't just pretty pictures. They were detailed blueprints, revealing the full, immense extent of these cosmic voids. We could finally see them not as theoretical constructs, but as tangible, colossal holes in the fabric of space. It was a technological wonder, a scientific achievement that allowed us to peer into the universe's grand design like never before. Thanks to new telescopes, we can finally see the universe's biggest empty spaces. Among these vast expanses, one particular void stands out as a grand anomaly, a cosmic desert that truly perplexed us, the Bootes Void. Discovered by Dr. Robert Kirchner in 1981, this colossal region, located in the constellation Bootes, stretches an unfathomable 330 million light-years across. To put that into perspective, where cosmologists would expect to find at least 10,000 galaxies, we've only identified a mere 60. This extraordinary emptiness is so profound that it initially appeared to contradict the very cosmological principle, the idea that the universe is homogeneous and isotropic on large scales. Adding to the mystery, the few galaxies found within the Bootes Void are arranged in bizarre, tubular formations, as if clinging to invisible threads. This great nothing is so empty, it challenges everything we thought we knew about the universe. It's a testament to the universe's capacity for surprise, a deep challenge to our understanding of how such a colossal absence could form. Then there's the Eridanus supervoid, another monumental expanse of nothingness, extending an astonishing 1 billion light-years across. This supervoid became a focal point of intense scientific interest when it was linked to one of the most mysterious features in the cosmic microwave background, CMB, the cold spot. The CMB, as we know, is the afterglow of the Big Bang, a nearly uniform warmth across the universe. Yet, in the direction of Eridanus, there's an unusually cold patch. Scientists hypothesize that as photons from the CMB traveled through the immense gravitational well of the Eridanus supervoid, they lost energy, a phenomenon known as the Sachs-Wolf effect. This energy loss would manifest as a colder temperature. A giant hole in space might explain the coldest, most mysterious spot in the universe. This potential causal link between a void and a CMB anomaly offers a tantalizing clue to the universe's earliest structures. And the list goes on. Consider the Keynes-Venatici supervoid, an even more incredible expanse, stretching for a mind-boggling 1.2 billion light-years in diameter. These supervoids, with their immense scales and profound emptiness, force us to confront a fundamental question. How could such massive voids have formed in the early universe? How did these colossal regions of nothingness come to be, seemingly defying the natural tendency of gravity to pull matter together? The sheer scale of these structures challenges our intuitive understanding of cosmic evolution and pushes the boundaries of our current cosmological models. How can a hole in space be bigger than 1 billion light-years across? The answer might change everything. One of the leading cosmological theories for the initial conditions of void formation points to a period just moments after the Big Bang, cosmic inflation. This theory proposes that the universe underwent an incredibly rapid, exponential expansion in its infancy. During this brief but dramatic inflationary epoch, tiny subatomic quantum fluctuations, mere jitters in the quantum foam of spacetime, were stretched and magnified to cosmic scales. These amplified fluctuations created regions of slightly higher and slightly lower density. Over billions of years, gravity then pulled matter into the denser regions, forming the galactic clusters and filaments of the cosmic web, while the less dense regions naturally expanded into the vast, empty voids we observe today. Tiny quantum jitters from the Big Bang might be why we have these massive cosmic voids. Another compelling theory suggests that dark energy, the mysterious force behind the universe's accelerated expansion, plays a crucial role in the growth of voids. Imagine dark energy not just pushing galaxies apart, but actively inflating the empty spaces between them. In this scenario, dark energy would exert a repulsive force, pushing galaxies away from regions that are already less dense. This would cause the voids to grow larger and emptier over cosmic time, effectively expanding them faster than the rest of the universe. Is dark energy actively creating these giant holes in space? It's a fascinating connection to one of the universe's greatest mysteries, suggesting that the very force accelerating our universe's expansion is also sculpting its vast emptiness. A more intuitive explanation for void distribution comes from gravity itself. Think of the universe's large-scale structure forming much like bubbles in a rising loaf of bread. As the dough expands, the yeast creates pockets of air. Similarly, in the universe, as matter, both visible and invisible dark matter, clumps together under the influence of gravity to form galaxies, clusters, and the intricate cosmic web, the empty spaces between these structures naturally expand and become voids. These voids are simply the regions where matter didn't coalesce, pushed apart by the general expansion of space and the gravitational pull of the surrounding denser areas. The universe grew like a giant loaf of bread, leaving massive empty bubbles behind. It's a powerful analogy for cosmic structure formation. Despite these compelling theories, the study of cosmic voids presents intractable challenges. The sheer immense scale and complexity of the universe make these regions incredibly difficult to observe and model. We're talking about distances so vast that light itself takes hundreds of millions, even billions of years to cross them. Furthermore, the elusive nature of dark matter and dark energy, which are thought to be the primary sculptors of these voids, adds another layer of difficulty. Their influence is profound, yet they remain largely invisible and poorly understood. Even with our best science, these cosmic voids are still baffling us. We're essentially trying to understand the universe's hidden architecture without being able to directly see the architects. Yet humanity's drive to understand the cosmos is relentless. Scientists around the world are employing advanced tools to probe these empty expanses. Powerful telescopes, both ground-based and orbital, peer deeper into the universe, collecting light from the faint galaxies that reside at the edges of voids. Sophisticated computer simulations, running on supercomputers, model the evolution of the cosmic web, attempting to recreate the formation and growth of these structures under different cosmological parameters. Data from surveys like the Sloan Digital Sky Survey, which has mapped millions of galaxies, continues to be a treasure trove, allowing researchers to explore voids and test the various theories of their origin. From giant telescopes to supercomputers, we're using incredible tech to map the universe's emptiness. This dynamic research is pushing the boundaries of our knowledge, bit by painstaking bit. The study of cosmic voids is not merely an academic exercise. It offers crucial insights for refining and validating our cosmological models. These vast, empty regions act as cosmic laboratories, providing unique insights into the roles and properties of dark matter and dark energy. By observing how voids evolve and interact with the surrounding cosmic web, we can test the predictions of different models of dark energy and dark matter distribution. Discrepancies between observations and predictions could signal the need for entirely new theories, pushing the frontiers of fundamental physics. These empty spaces are actually helping us understand the universe's darkest secrets. Voids are, in essence, the negative space that defines the positive, allowing us to better understand the universe's composition and evolutionary history. But what if the truth of cosmic voids is far more radical, far more mind-bending? Some highly speculative theories propose that voids aren't just empty spaces, but rather interfaces or even gateways to alternate universes. Rooted in multiverse theory and drawing on concepts from quantum mechanics and string theory, this idea suggests that our universe might be just one of countless bubbles in a vast cosmic foam. Perhaps, these theorists posit, the boundaries between these universes are thin, and certain extreme regions, like colossal voids, could be where these dimensions ripple or even touch. What if these cosmic voids aren't empty, but secret doorways to other universes? It's a provocative concept that pushes the boundaries of our imagination, suggesting a reality far grander and stranger than we can currently comprehend. Another speculative idea connects voids to the very earliest moments of the universe. It hypothesizes that quantum fluctuations in the primordial soup of the early universe, those tiny, fleeting energy jitters, were not just stretched by cosmic expansion, but left indelible quantum imprints on the fabric of spacetime. These imprints, representing slight variations in energy density, would then have guided the subsequent distribution of matter. The regions where matter was less likely to accumulate due to these quantum imprints would have naturally expanded into voids, essentially becoming ancient echoes of the quantum chaos of creation. These cosmic voids might be fingerprints left by the quantum chaos of the Big Bang. It's a profound thought, that the smallest scales of reality could dictate the largest structures of the cosmos. Taking a step further into abstract physics, some theories propose that voids could be topological anomalies or space defects within the very structure of spacetime. Imagine spacetime not as perfectly smooth, but with microscopic irregularities, like tiny tears or wrinkles, inherited from the universe's rapid inflationary period. These theoretical defects could have acted as regions where matter simply could not accumulate, preventing the formation of stars and galaxies. They would be inherent flaws in the cosmic fabric, primordial absences that grew with the universe's expansion. What if the universe itself has defects that create these giant empty spaces? It's a mathematically elegant, if challenging, concept that suggests voids are not just lack of matter, but fundamental properties of spacetime itself. And what if voids aren't empty at all, but teeming with a hidden population of objects? One intriguing speculation suggests that voids may be filled with primordial black holes. These are theoretical black holes, much smaller than stellar mass black holes, believed to have formed in the extremely dense conditions shortly after the Big Bang. If they exist, and are numerous enough, these undetectable black holes could gravitationally clear their surroundings, pushing away gas and dust, and contributing to the immense emptiness of voids. They would be the silent, invisible architects of these vast cosmic deserts. These empty voids might be hiding millions of invisible black holes. It's a tantalizing thought that the most desolate regions of the universe could, in fact, be home to a hidden, powerful, and utterly unseen population. Finally, let's consider dark matter filaments. We know dark matter forms an invisible scaffold, guiding the formation of the cosmic web. What if, under certain conditions, these dark matter filaments could collapse or even disintegrate? Such a disruption to the flow of matter and the gravitational forces would leave behind vast, expanding empty expanses. Imagine the cosmic web as a delicate, invisible structure, and if parts of that structure falter, the surrounding empty regions would grow even larger. What if the invisible scaffolding of the universe collapses, leaving behind these giant holes? This theory offers a dynamic role for dark matter, not just as a static gravitational anchor, but as an active, evolving component in shaping the universe's grand, empty spaces. So cosmic voids are far from mere barren wastelands. They are treasure troves of clues, forcing us to rethink the cosmos and pushing the boundaries of our understanding. Whether they are the amplified echoes of quantum jitters, the result of dark energy's relentless push, the natural consequence of gravity's clumping, or something far more exotic like gateways to other dimensions, or hiding places for primordial black holes, their study is fundamentally reshaping cosmology. Voids act as silent guardians of the universe's deepest secrets, challenging our assumptions and revealing the profound complexity of reality. These empty spaces are actually hiding the universe's most profound secrets. And as we continue to peer into their depths, we uncover not just emptiness, but the very principles that govern existence itself. And yet, as we unravel these mysteries, a deeper, more profound question inevitably arises, one that truly challenges the limits of human comprehension. What was before the Big Bang? We speak of the Big Bang as the moment of creation, the genesis of space-time, matter, and energy. But if time itself was born in that cosmic explosion, does the concept of before even apply? Was there a preceding state, a precursor, or was it truly an absolute beginning from nothing? This isn't just a scientific question, it's an existential one, probing the very fabric of reality and our place within it. If the Big Bang created time, what the heck was there before numbs the Big Bang? It is the ultimate question, the greatest unknown, and it invites us to explore the most speculative, mind-bending theories that physics has to offer. We've journeyed through the universe's vastness, witnessed its inevitable decline, and grappled with the terrifying possibilities of its ultimate demise. But now we stand at the precipice of the most profound question of all. What came before? What if the Big Bang wasn't a singular event, but merely a cosmic breath in an eternal cycle? This is the core of the oscillating universe theory, a captivating idea that suggests our cosmos is a grand, rhythmic dancer, expanding and contracting endlessly. Imagine it, a universe born from a Big Bang, only to eventually halt its expansion, reverse course, and collapse back into an infinitely dense point, a big crunch. But instead of an end, that big crunch then ignites the spark for another Big Bang, giving birth to a new universe, a fresh cycle, an eternal cosmic heartbeat. It offers a kind of philosophical comfort, doesn't it? The universe, in this view, has no true beginning, no ultimate end, just an infinite, majestic dance of creation and destruction. Yet, as with many elegant theories, the oscillating universe faces significant challenges from our current understanding. For all its poetic appeal, this model doesn't quite align with the data we've gathered. The most critical flaw lies in our observation of accelerating cosmic expansion. We've seen that dark energy is not only pushing galaxies apart, but doing so at an ever-increasing rate. This relentless acceleration makes a future contraction, a big crunch, highly improbable. Current cosmic microwave background data, our oldest snapshot of the universe, also doesn't support the specific conditions required for a perfectly cyclical, bouncing universe. It forces us to confront the limitations of even our most cherished ideas, pushing us to seek deeper, more complex explanations for cosmic genesis. If our universe isn't simply bouncing back and forth, then perhaps it's not alone. This brings us to one of the most mind-bending, awe-inspiring concepts in modern cosmology, the multiverse theory. Imagine our universe, not as the entirety of existence, but as a single, fragile bubble floating in an infinite cosmic foam. This theory posits that countless other universes exist, each a separate bubble, potentially with its own unique physical laws, constants, and dimensions. Some might be vastly different from ours, perhaps with different forces, or even different numbers of spatial dimensions. And critically, these bubbles aren't static. Some versions of the multiverse suggest that the interactions or collisions of these cosmic bubbles could be the very spark that ignites new Big Bangs, perhaps even our own. It's a vision of infinite possibility, where creation is a continuous, sprawling process across an unimaginable cosmic ocean. But this grand vision, for all its profound wonder, comes with a stark scientific challenge. The multiverse, by its very nature, is incredibly difficult to test. If these other universes are truly separate bubbles, beyond our cosmic horizon and perhaps even beyond our space-time, how could we ever detect them? How could we gather empirical evidence to prove their existence? This untestability has made the multiverse theory a subject of intense debate within the scientific community. While it offers elegant solutions to certain cosmological puzzles, the lack of direct observational evidence leaves many scientists cautious. Is it a brilliant scientific hypothesis, or a philosophical construct beyond the realm of empirical science? This question pushes us to the very limits of what we can know. To truly understand the Big Bang and what might have preceded it, we must confront a fundamental conflict at the heart of modern physics. We rely on two monumental theories: quantum mechanics, which governs the bizarre world of the very small, particles and forces at the subatomic level, and general relativity, Einstein's masterpiece, which describes gravity and the large-scale structure of spacetime. Both are incredibly successful in their respective domains, but at the Big Bang singularity, that infinitely dense, infinitely hot point from which our universe sprang, these two pillars of physics break down. They give conflicting, nonsensical answers. This profound clash tells us that our current understanding is incomplete. We need a unified theory of everything, a theory of quantum gravity, to truly peer into that moment of creation and understand what happened, or didn't happen, before. One of the most elegant attempts to resolve this singularity problem comes from the brilliant minds of Dr. Stephen Hawking and Dr. James Hartle. Their no-boundary proposal suggests a universe that is finite but without a boundary, much like the surface of the Earth. If you walk on Earth, you never reach an edge, yet it's not infinite. Just like the space-time, this theory posits that the Big Bang wasn't a sharp, infinitely dense point, but rather a smooth, rounded transition, like the North Pole on a globe. At the North Pole, there's no north of north. Similarly, the Big Bang in this model would have no before. It elegantly sidesteps the need for a beginning in time, effectively rendering the question of what came before meaningless, because time itself would have simply emerged from this smooth, beginningless state. Venturing deeper into theoretical physics, we encounter string theory, a framework that proposes the fundamental constituents of the universe aren't point-like particles, but tiny, vibrating one-dimensional strings. These strings vibrate in different ways, giving rise to all the particles and forces we observe. Crucially, string theory often requires the existence of extra-spatial dimensions beyond the three we perceive. Within this framework, a fascinating pre-Big Bang scenario emerges. What if our universe wasn't born from nothing, but from the catastrophic collision of two massive multidimensional membranes, or branes, floating in a higher dimensional space? Imagine two cosmic sheets, possibly existing within a larger multiverse, crashing into each other. The immense energy released from this collision could have been the very Big Bang that inflated our universe, a genesis from another realm entirely. Perhaps the most counterintuitive yet scientifically compelling idea is that our universe arose spontaneously from nothing, in a quantum sense. This is the theory of vacuum fluctuations. According to quantum mechanics, even seemingly empty space, a quantum vacuum, is not truly empty. It's a seething, bubbling soup of virtual particles constantly popping into and out of existence. In this model, our universe could have originated from a tiny, infinitesimally small bubble of false vacuum within this quantum foam. This false vacuum would have possessed an inherent energy, a kind of negative pressure that caused it to rapidly inflate, expanding exponentially in a process known as cosmic inflation. From this initial, spontaneous quantum fluctuation, a universe, our universe, could have burst forth, seemingly out of nothingness, driven by the inherent instability of the quantum realm. Moving back to cyclical models, but with a more modern twist, we encounter the Big Bounce theory. Unlike the classical oscillating universe, which faces issues with entropy, the Big Bounce offers a non-singular cyclical model. It suggests that our universe wasn't born from an infinitely dense Big Bang singularity, but rather from a previous contracting universe that reached a minimum, incredibly dense, but finite size, and then bounced back elastically. This rebound, driven by quantum gravitational effects, would have initiated a new expansion, giving birth to our current universe. It's a universe that breathes, not collapsing to an absolute zero point, but rather recoiling from a quantum squeeze, perpetually regenerating itself, an eternal cosmic rhythm without true beginning or end. And then, for a truly mind-bending possibility, some physicists speculate about black hole universes. This theory suggests that the singularities found inside black holes, those points of infinite density, could actually be the seeds for new, expanding universes. Imagine our universe not as a standalone entity, but as the interior of a black hole existing within a larger, parent universe. And conversely, the black holes within our Ratian universe could each contain their own nascent universes, creating an infinite, nested hierarchy of cosmic realities. It's an idea that challenges our perception of scale and existence, implying that the very fabric of our reality could be an enclosed pocket within a grander, unseen cosmic structure, forever linked to the gravitational maw of another realm. To delve deeper into the Big Bounce and other non-singular origins, we must turn to loop quantum gravity, or LQG. This ambitious theoretical framework attempts to reconcile the seemingly incompatible worlds of quantum mechanics and general relativity. LQG suggests that space-time itself isn't a smooth continuum, but is made up of discrete, tiny, interwoven loops, a granular structure, much like a fabric woven from invisible threads. When loop quantum cosmology, or LQC, applies these principles to the entire universe, it offers a specific, quantum mechanical description of the Big Bounce scenario. It provides a mathematical framework for how a contracting universe could reach an extreme density and then, instead of collapsing into an infinitely problematic singularity, rebound into a new expansion. Within loop quantum cosmology, the transition from one universe to the next is described as a, quote, quantum bridge. This isn't a violent, destructive collapse followed by a sudden, inexplicable reignition, but a smooth, continuous, albeit dramatic, process. The universe undergoes a quantum leap, a phase transition where the forces that govern it at extreme densities cause it to effectively bounce back. This quantum bridge connects the contracting phase of a previous universe to the expanding phase of our own, entirely avoiding the problematic singularity. It suggests that the past universe didn't end in a point of infinite density, but rather transformed, through a quantum mechanism, into our current expanding cosmos. It's an elegant solution that offers a continuous cycle of existence without ever breaking the laws of physics. So here we are, at the very edge of human understanding, peering into the genesis of everything, from the rhythmic breath of an oscillating universe to the infinite bubbles of the multiverse, from the smooth emergence of a no-boundary cosmos to the violent collision of brains and the quantum foam that births universes. We've explored the most audacious and profound theories about our cosmic origins. While many of these ideas remain speculative, they are not mere fantasy. They are the rigorous, imaginative efforts of humanity to make sense of the greatest mystery of all. Each theory, each hypothesis, enriches our understanding, challenges our assumptions, and pushes the boundaries of what we thought possible. The truth is, we may never definitively know what came before the Big Bang, or if before even applies, but the beauty lies not just in finding the answers, but in the relentless, unending quest itself. Every question we ask, every observation we make, every theory we devise, reveals more about the incredible universe we inhabit, and, by extension, more about ourselves. Our journey through the Sentinels of Sapience is a testament to humanity's enduring curiosity, our insatiable drive to understand. The cosmos is boundless, its secrets infinite, and our search for truth will continue, forever propelled by wonder, into the vast, uncharted future.